Okay, so we're going to get started now. The first thing I wanted to cover today was material that was addressed on the take-home exercise that I gave you. And that take-home exercise included two basic components. One of the components focused on this issue of delays within a system as represented by successive levels of sort of chained stocks, what we sometimes call aging chains. So here we're dealing with a situation where with a first order delay, we have some stock here, and we'll have perhaps an inflow and an outflow. And why do we call this a delay? What did we see last time? That sort of illustrates why it's a delay. What's the delay of what?
Where inflow equals outflow, maybe?
Good. So yeah, outflow is a delayed version of inflow. So if we had flow in that sort of went like this, we would see a flow out that looked like what?
Would be more curved.
Yeah, okay, and where would it, so it would start at 0, since with no inflow, we'll assume the stock is initially at 0, it's starting at 0. And then how would this change over time? So I heard curved, and that's correct. Is it like that, or?
Like a log function.
Okay, good, it's a little bit, okay, yeah, so it goes something like this. And this curve is actually, there's actually a mathematical formula for this. It's in this simple system. So if we posit that there's some mean time, I'll call it tau, maybe I'll continue to call it tau, though often people will use mu instead. And so that's some constant, some sort of mean time you spend in the stock. What's the formula for outflow?
P over tau.
Okay, it's x over tau. And what I'm hearing is understandable because there's two different ways of phrasing this. One is with a mean time, and I just said that this was measured in time, in which case this is x over tau. Why does it have to be that dimensionally? Why does it not make sense for this to be x times tau? So if this is units of, let's say, persons, and if time is measured in years, what do the units of a flow have to be from a stock that's persons? Person per year. Remember, this is the rate of, it's associated with the rate of change in the stock. You sum up all the flows, you sum them so they all have to have the same units. It doesn't make sense to add a person to a time. They all have to have the same units. So you sum them up, and what you're going to get is the rate of change of the stock. And so the flows all have to be associated, if the stock is associated with units T, the flows have to associate with units, A, the flows have to be associated with units A over some unit of time. After all, they change over time. So the units of this are correct here. They're persons per unit time, and therefore, if tau is a time, this has to be x over tau. What's the other way of phrasing it? We could, instead of specifying as a time, we could specify what? A chance of leaving per unit time. It's actually, one has to be careful, it's not a probability. It can easily be greater than 2, or greater than 1, excuse me. It can't be less than 0, but it can be greater than 1. And it's a probability per unit time. What would it mean? Well, you tell me. What's the relationship? If we phrase this instead, I'm going to write it down here so we're not confused. I'm trying to review this before any exams on it, where this could feature prominently. So we have an inflow and outflow. If I wanted to specify that same system using instead a probability per unit time of advancing alpha. What would alpha have to be for these to be the same? Okay, yeah, it's equal to 1 over tau. And what's the formula here for that? If this is probability per unit time, that I'll give you a hint. That's of dimension 1 per unit time. Let's say 1 per year if we're being concrete. In other words, 1 per unit time is the dimension of that. It's a probability per unit time. So what's the formula for this have to be? Yeah, alpha times x. Alpha is persons, this is per year, say. We read that as kind of per year, so this is going to be units persons per year, which it has to be for this to be persons, of unit person. So it's got to be the case. It's one easy way to remember it. But look, if you're dealing with a chance per unit time, it's got to be the stock times that chance per unit time. Okay, so this is like a 5% chance per year that you'll graduate. No. No, we won't say that. A 5% chance per year that you will go on to the career of your dreams or whatever. Okay, so if that were the case, on average, in how long would you go on to the career of your dreams? So again, we're going back and forth between these. One is I heard it earlier, the reciprocal of the other. Tau is 1 over, so given an alpha, given a chance per unit time of doing something, the average time before you do it is 1 over that alpha. And alpha is 1 over tau. So given a mean time until something happens, if it's in a first order delay context, alpha is 1 over tau. Are we okay with that? Okay. Okay, so ladies and gentlemen, this curve here can be phrased as either it's ladies and gentlemen, 1 minus this curve here, e to the minus alpha times, and if this occurs at time t0, this kind of transition in the inflow, it suddenly shoots up, vt minus t0. Okay. Alternatively, I could phrase it in terms of tau. How would I rewrite this in terms of tau? All that changes is this area. What does it change to? Specify it to me in terms of tau.
Just replace the alpha with 1 over tau.
Good. Not only good, great. Remind me your name? Andrew, yes. Your reputation precedes you. Great. So we call alternatively represent. Let's reason this through. 1 minus this thing. So anyone remember? If you have a 0 here, let's consider time t0. This is a 0. What's e to the minus alpha times 0? Well, it's e to the 0. It's whatever alpha is, multiplying it times 0, as long as it's not an infinite number, it's going to be 0. What's e to the 0? Anyone remember? 1. So the value is going to be what at that time? 1 minus 1 or 0. If we look really, really far out, this is going to be some really huge, big number, some god-awful big number. And we're going to have e to the minus some big number. What's that going to be very close to? It's going to be very close to 0. Why? Because if you have e to the minus, if you have e to the minus a in general, you have some a, and e to the minus a equals what? 1 over e to the a, right? So this thing is really huge. This is like 1 over some e to that thing is, man, if that's big, this is like gargantuan. You know, as they say, New York City is big, but we are big R. This is so good for big R. So, you know, this is big R, then e to this is going to be even big R, and 1 over that is going to be super small. Okay, so ladies and gentlemen, this is going to be super small. It's going to be 1 minus a super small thing, so it's going to be very close to 1. So if this shoots up to 1, you know, now if the value of the inflow shoots up to I, instead of 1, then what we're going to have is I times this whole thing, or I times that. Okay, that's where it's going. Okay, fair enough. It's good to know about this. Question? Oh, thank you. The screen blank. Okay, great. Okay, ladies and gentlemen, first order delays. The outflow is a delayed version of the inflow. So, I asked you during your take-home exercise to now turn this into multiple levels of delays. And the first of them we actually created in this very classroom before you left. And what did it look like?
Like two first level.
Good, they're just strung together. And this was kind of the overall outflow, right? And if you want to start getting ready, I'd suggest that you get your AnyLogics up now so that we are primed to go, okay? And we can start to do a bit of engage in frobbing behavior in just a minute. Okay, so ladies and gentlemen, so we had a second order delay like this. This was the overall outflow. And we had a mean time, call it tau, to traverse the system. And so each of these halves of the system, these two halves, each had how long to traverse them, so that the time across the entire system was tau. Yeah, each had half, because in order to get across the whole system, you have to get across the first half, and then after you're done with that, get across the second half. So the total time across the system is just the sum of the time across each of these subsystems. So each of them is going to have a mean time across it of a half. And that's why I asked you here, if we call this x1 and x2, I asked you to have a formula here that was what? X over half of t. Remember, if this was x over t, how long would it be until you leave on average? Sorry, over tau, that constant. If this was x over tau, how long would it be on average till you leave this?
Twice as long.
Well, yeah, it would be ton tau. Here we're making it over tau over 2. So on average, you leave this, and on average, you traverse this in tau over 2 time. And same thing here. This is x1, this is x2 over tau over 2. There we go, ladies and gentlemen. Okay, great. Oh, that's horrible. One time when I was young, I know, you probably think we were using rocks. I was playing with the other Homo habilis, making stone tools. But no, actually, we had a thing called pens at that time, and I was taught script, and I got a very bad grade in script, the worst grade I've ever gotten. I got a D in penmanship. Sorry, confession. And I have never quite lived it down. And unfortunately, my students have been forced to suffer accordingly. I didn't anticipate that part of it. Okay, ladies and gentlemen. So here's x2 over tau over 2. Okay, and so you traverse this one in tau over 2 time, this one in tau over 2. So the entire thing you traverse in what time, on average? Tau. Good. On average. But the distribution is going to be changing. How is it different when you have two things strung together in terms of how quickly people start coming out here compared to when we just have that one over there with a single layer? How is it different? Glad in the SEEQ, the SEEQ, the standardized evaluation, there's nothing for penmanship. And then I'd really be in trouble. Okay, ladies and gentlemen. So how does if we have here an inflow that goes like this, what is the outflow going to do here? Is it going to do exactly the same thing as over there? No, actually it's not. In fact, there's not going to be as many people coming out of it early on, and it's gonna take a little bit of time before it really starts rising up. Now let's suppose we put together 3 of these in a row. I asked you to do that. 3 of them in a row. How is it going to be different? Yes?
What are the equations determining the flow?
Okay, so these are the formulas here. Determining the
Just
flow.
x1 over tau.
X1 over tau over 2.
Tau over 2, okay.
That important. It's important that it's tau over 2, so that the mean time in this state is tau over 2.
Okay.
And same thing with this, x2 over tau over 2. And in fact, we did this in the closing minutes of the last session. I don't know if you remember this, but we had a first order delay, and then we created a second order delay. Here we go, second order delay. And I believe that you accompanied me and said exercise. Here we go. Here's our second order delay. How does this differ in terms of the overall outflow as a function of the inflow? Remember, we said over there, that the outflow is just the delayed version of the inflow, but kind of curved in a most pronounced fashion. Here, what is the relationship between the overall outflow and the inflow? If we were to plot this out on a graph as we had arranged, how would it be different?
The outflow or the inflow for the overall outflow is changing because it's based on the outflow of the first outflow.
Good. So in order to get through, you have to first go through the stock there and then out. Ladies and gentlemen, this is what's called a memoryless process. You come in, it doesn't matter how long you've been in the system. You come in and you have the same chance per unit time of leaving. What is that chance per unit time of leaving? Alpha or?
1 over tau.
Good man. 1 over tau. Yeah. Alpha is 1 over tau. You can view this in terms of alpha, or you could write it in terms of tau. There are 2 different ways, mathematically identical ways of writing this. Because if the mean time in the state is 1 over the chance per unit time of leaving the state. For this is memoryless. No matter how long you've been in here, as long as you're still in the state, still in the stock, you have that same chance per unit time of leaving of alpha. Doesn't matter how long you've been in there. This is said to be, mark my words, it is said to be well mixed, meaning we treat it as homogeneous, meaning we treat it as the people in there is indistinguishable. We're not keeping track how long they've been there. Their chance of leaving is the same. Now, there's some systems for which that's a pretty good approximation. But there's systems where that's a poor approximation, where it's not really accurate. And among them, I'm pleased to say, are student trajectories. Why do I say that your characterization of your graduation as a memoryless process, a process that doesn't matter how long you've been here, is not a very good approximation? Why do I say that?
There's lots of different tracks that you can take.
Lots of different tracks, and hopefully, year after year, you're taking successive courses, and after going through, you're making progress. That very notion runs afoul of this. We're not making progress here. We're just sitting in this state, and we have the same kick of the can of graduating. It's like we're in a lottery every year, and they pick who graduates, which would be an unfortunate circumstance. Believe me, whatever you think of our marking, it's not that bad. Okay? Okay. Wow, Andrew's graduating. but he just came in. Well, you know, he won the lottery. Here's his PhD degree. Great, okay. That's not how a lot of systems work. I mean, in a situation of students, the traditional model was at a university, you're there for 4 successive years and then you graduate. And so treating it as well mixed, that no matter how long you've been here, you have the same kick of the can, the same chance to graduate in the next month, is a very poor approximation to the life of the student. Would you agree? So, I mean, you would be dismayed if I, took a photo. When I was teaching at MIT, they used to give us photos before the class of every student in the class. And we can kind of like, oh, so that is. And then when they came in, I know kind of who they were, and I could have conversations with them. Imagine if I took photos of each of you and I stuck you here, and I said, okay, you're in a first order delay with respect to your graduation. Would you be happy? No. Not so much, because you could be here for 10 years and you still haven't graduated. Sorry, you didn't win the lottery this time, Andrew. Better luck next year. Right? That would be a depressing situation. Ladies and gentlemen, a lot of systems are better approximated by a non-memoryless process. Is this process memoryless? Does it, for someone's chance of leaving this system, leaving the whole system in the next little bit of time, does it matter when they came in? Suppose someone just came into the system. Where are they more likely to be? X1 or X2? X1. Someone was in X1, in the next little bit of time, for them to leave the whole system, they would have to be extraordinarily lucky. Not only would they have to get out of X1, but they'd have to get through X2 really quickly, right? So it's very unlikely they'd get through both.
Wouldn't the chance depend on tau?
Yeah, the chance will...
If it was over 50%, chances are they're in X2.
That's right. Exactly. Exactly. Well spoken. Your name?
Jordan?
Jordan. Yes. I've enjoyed the pleasure of including you in other courses, and that's darn right. So if they've spent more than tau time here, tau over 2 time, they're more likely to be in X2. And so, ladies and gentlemen, in a lot of systems, when we try to model them, we don't model them with a single stop. We model them as a series of stops. This, ladies and gentlemen, is what we call stateless, not in the sense of, not being able to secure immigration to any country. Sorry, there's a better word is memoryless. Memoryless, okay? It's a memoryless process. This over here, is this memoryless? Does this, I mean, that one doesn't keep track. It's memoryless in the sense that it doesn't remember when you came in. That is irrelevant for your chance of leaving per unit time. Your chance of leaving per unit time is what here? Alpha. Thank you. Thank you. Your chance of leaving, regardless, is your chance of leaving here independent of how long you've been here? No. It needs to remember how long you've been here. And guess how it remembers it? With 2 successive stocks. You're more likely to be here than here, okay? So let's take a look at this. Let's take a look at this. I'm going to actually do it, to cut to the chase, I'm going to do it for the 3-stock model, because it will be more evident yet. So here's our 3rd order delay model, which I hope you folks have created in your own company. Okay. So here's a 3rd order delay. So here we have the 1st order delay as a building block that's repeated how many times? 3. Here it is repeated once. Here it is repeated twice. Here it is repeated the 3rd time. Why do I say it's repeated? Well, each case, it's the value of the flow is just the stock divided by this parameter. So it is for the second one. So here, it's divided by this parameter divided by 3. It's divided by sort of the per stage amount of time. Same thing here, except it's this stock divided by it. Same thing here. Okay, so if we were to run this, what would we see? Let's run it with a high leaving hazard. What are we going to see? How does it differ for the 1st order case? How is that different? How is this different from the first order case, ladies and gentlemen? This is with a very small delay. Well, let's go back to the first order case and compare it, okay? So here, with a high leaving hazard, we have a mean time in system of 1. And here we're going to go open this up. This was an earlier version. I'm going to open up the version which had it specified as, here we are, in the same mathematical way, the same way with a mean time in the system. Okay. Okay. Here we go. Okay. Come on. First order delay model. Here we are. Okay. High leaving hazard. And the alpha is 0.5 there. Okay. And if we were to run this, we have a graph up top. If we were to run this, what would we see? Well, we'd see something that had some similarity. After all, the inflow is sort of going up and down and up and down. But you see that it actually takes quite a bit of a longer time. Some of them transition soon, hence it's going down here. Some take much longer to transition. The average time to transition is still 2. It's just that it's much more spread out here compared with the third order delay. Okay, let's go to the third order delay again, and we'll show this. And here, there's a more uniform time. There's less spread among them, okay? We don't have the sort of extremes that we might think, okay? And unfortunately, this is, I'd really like to run them alongside each other. But here, the average time is 2. You have fewer outliers that take a long period of time to spread. What I would invite you to do, and I'm going to see if this might be feasible, perhaps this will be inadvised, is I'm going to see if I could copy from here. Boom. Copy. I selected it, and I'm going to do copy. And then I'm going to go over and see, and I'm going to tempt fate with this because I've never done it before with this particular model or with models with clashing variables like this. I'm going to go over to the first order delay model, and better yet, let's copy from here. Copy the simple system. Don't copy the complicated system. Copy the simple system. So I just copied this. Copy. And I'm going to paste it into the third order delay. I should have asked you to do this for your assignment. There we go. Great. So here we go. We're opening it up, and let's paste in here. Boom. Oh my gosh. Okay. Use the arrow keys to move it around. Okay. Great. Now we're cooking with gas. So right now this outflow is specified as alpha times p. We don't want it in terms of alpha. We want to use mean time over system. So you're going to tell me, I'm going to delete alpha. Alpha is gone. I'm going to connect this up. What is the formula for outflow going to be? For the mean time in the system for this guy to be the same. Exactly. So P over mean time in system. So now we have them side by side running, ladies and gentlemen, in tandem. Okay? This is starting at 0. This guy is now P over mean time in system. Now, I'm going to plot out on this graph. So how did I do that? I opened up the other one. I went here. I pasted it. Notice it renamed the variables to prevent clashing. I went here. I got rid of alpha and made this instead depend on mean time in system and made the outflow be P over mean time in system. That is exactly this first order delay over here when phrased in terms of tau. Tau is mean time in the system. It's the mean amount of time you spend there. Now, to complete this, I'm going to go up here and I'm going to have this also display the outflow, and I'm going to, maybe I'll rename this guy here. Instead of calling it outflow, say outflow from first order delay. How's that? Good. Outflow from first order delay. Now, it makes it clear. Names are important, ladies and gentlemen. In software engineering, including modeling by extension, names are important. I just renamed this. So instead of generically saying outflow, which is subject to a lot of interpretation, after all, there's a bunch of outflows, I just named it outflow from first order system. Okay, great. And now we're going to add to this plot outflow from the first order delay. Great. And what will the value be? It will be, okay, and I'll give it a better name. Outflow from, this one can have lots of words in it, first order delay. There we go. Okay, so now having done that, our assumptions will, or changes to mean time and system, changed assumptions will modify both. And guess what we're going to see? We're going to be able to look alongside this guy and this guy. Okay? Probably I should name this overall outflow to indicate it's coming from a third order delay. Great. Here we go. And what do we see here? Well, we see that they are diverging, ladies and gentlemen. How are they diverging? Well, the overall outflow, the one from the third order delay, is brought down. It's somewhat tighter. The average time is still the same, it turns out, but there's less high numbers that are leaving late. Okay, it turns out that somewhat more for the first order delay are leaving a bit earlier. So if we were to zoom in, and I don't know how visible it's going to be, but if we were to zoom in here, and I'm going to try to see if I can zoom, go to view here. Here you can see them cross. So you can see with the first order delay, the purple one, if indeed that's purple. Is that purple or is it lavender or fuchsia? I don't know. I lost. Okay. Okay, you see this? The purple one, more leave early and more leave late. The average is going to be equivalent between them, but the third order delay has fewer people leaving early and fewer people leaving late. In other words, it's more uniform. And guess what? As we increase the number of stages of this, keeping constant the time across the entire system to tau, what's going to happen? And more uniform. Exactly. So, ladies and gentlemen, what we're going to see here is that as you get to higher orders of delay, we call these kth order delays, first order, second order, third order, fourth order, fifth order. And as you go up, this is first order, second order delay, you're going to be getting an outflow from a two-stage system here. If you have a so this is in a situation where we have it starts with people in the system only at stage one. You're going to see this sort of go up and then down. Early on, if everyone starts in stage one, why is it that few people are going to come out early on of the system?
There's
Few people in stage two. And so it's going to have to fill up before it decreases. So it's going to fill up later. In contrast, ladies and gentlemen, if you have people start in the system with a first order delay, they're going to be leaving immediately from the whole system. Here, to leave the whole system, you've got to transition across these two stages. How about with a third order delay? Well, now you could see, this one heads up immediately. With a third order delay, it's going to sort of go up more slowly. There's actually sort of a little bit of a uptick here where very few people go out. And in general, as you go through higher and higher numbers of stages, just as what was said, you're going to get something closer and closer to the actual value. The variance is going to be decreasing here, okay? The likelihood of still being in the system is going to be going down, and increasingly you're going to be transitioning in time closer and closer to the actual mean, okay? And it turns out that there's some theory associated with it. These are called Erlang distributions here, and as time goes is the number of stages goes up, they're going to become tighter and tighter. As the number of stages goes to infinity, keeping constant tau, what are we going to get closer and closer to? Well, it's called an infinite order delay, this kind of idealized situation where so this is in an infinite order delay, so I'll set this out, infinite order delay, okay? There we go. If we have that, and we have the inflow go up at one time, what do you think the outflow will do? If it's time tau, here's time tau, what do you think it's going to do? Well, it turns out it's an infinite order delay, it's going to go up exactly time tau after it. This will be exactly delay of tau of the outflow from the inflow. If you had enough, if you got 100 stocks in a row, and I would invite you to, I admire ambition. If anyone wants to do it, I'll give you extra credit. But with an average time of tau, you're going to get very close to a perfect delay. So in short, ladies and gentlemen, a stock by itself, a single stock is memoryless. It's leaky. It assumes everything is well mixed. No matter when you came in, if you came in a short time ago or a long time ago, you're going to have the same chance to leave. With a second order delay, we start to put that aside. If you just came in and you're in this stage, you just came into this stage, your chance of leaving in the next little bit of time is quite small. Leaving the whole system in that same little bit of time is quite small. If in a third order system, it's even more so. If you start here, you just came into stage one, your chance of leaving initially is very small. And the more stages you get, the more and more this is going to approximate a perfect delay. So these are called aging chains and higher order delays. And they're often strung together to avoid this effect that as soon as you come in, you're going to start to leave. So, ladies and gentlemen, we've been talking about this awfully abstractly. How would this be appropriate? Well, we mentioned one example, one application, right? You're modeling student progress. This would be a horrible thing. If the U of S asked me to, model student dropout in the U of S, right? Some people graduate and some people drop out. When I modeled it like this, it would lack face plausibility. It would really abuse the situation in terms of serving as an approximation. If we start to put in place multiple stages, we could better capture the sort of progression, the fact that second year in computer science has traditionally been a very tough year. There may be more attrition there, or more individuals who don't continue, whereas third and fourth year, the students by and large tend to continue. Here we've only got single outflows. It doesn't matter how long they've been in there, we treat them with the same chance per unit time. So often we end up structuring our system in this way. Give me another type of thing that is awfully dependent on how long you've been in a state. Well, if we consider, for example, the chance a car will break down, right? How long you've had that vehicle is going to have a big impact on a chance per year of needing to be taken off the road because its engine clogs out. And actually there it's a U-shaped curve. There's some duds up front that might get discovered, you replace it early, and then after that they might last for years and years. If you were interested in emergence of diseases in people, there's often much time between someone's infected and when an illness of obvious symptoms come up, or between how long they've been living and chronic diseases come up. So for a lot of systems out there, from whatever domain, a memoryless approximation, an approximation that just depends on a single stock, is just not going to cut it. You represent these stages, and the stages capture state. This is going to be very important, ladies and gentlemen, very important when we talk about agent-based modeling, because agent-based modeling is going to treat state in a different way than system dynamics. Remember, in system dynamics, aggregate models like these, we divide people up. If we're dealing with a population, we divide them up by their state. And then within each compartment, within each category, we treat it as being well mixed, homogeneous. Doesn't matter how long you've been there. In agent-based modeling, we're going to instead divide up the model by individuals, each of whom keeps track of their own state. And we're not encumbered by this memoryless assumption. The way we capture situations that are stateful, that are not memoryless, where it does depend how long you've been in a state for you to leave, we divide them up into different stocks, and often it's successive stocks here. Okay? So you should know this notion of that a single stock is memoryless. It doesn't matter how long you've been there. You have the same chance per unit time of leaving. And if you want to capture state, if you want to capture memory of the system as to how long you've been there, because your chance of dropping out depends how long you've been in the program, your chance of graduating does, you want to divide it up into different states. Does that make sense? So if we want to capture systems in the world that are stateful, we often do so with multiple successive compartments, multiple successive stocks. Okay, so that was that point of that exercise. It actually does matter. And so, here's an example of a model. These are individuals with early stage kidney disease, medium stage, later stage, start to get to kidney failure, and individuals who are on dialysis. They progress, and a doctor can have a lot more impact if they catch them early and treat them early rather than if they treat them late. So yet another reason to sort of divide them up. Okay, that's great. So ladies and gentlemen, we are going to go on. Having recorded that, I am going to go on to another very important topic which I asked you to explore in your